So hello students, in this video we are going to talk about an important concepts of nuclear chemistry, that is nuclear stability and modes of decay. There are several theories used to describe the stability of nucleus, but in this topic we are going to talk about qualitatively how a nuclear stability is established, and if a nucleus is radioactive, not stable, how it is going to decay in order to become stable. So we know that inside, inside a nucleus we have neutrons and protons. This is nucleus within which we have neutrons and protons. For nuclear stability, a proper balance a proper balance between neutrons and protons is required. If there is imbalance, between number of neutrons and protons, then nucleus becomes unstable. And it decay. During the decay process, interconversion between neutrons and protons takes place, and that gives rise to stability of nucleus. So nuclear stability is obtained by interconversion of neutrons to protons and protons to neutrons by decaying radioactive particles. So it is the neutron to proton ratio. It is the neutron to proton ratio that determines the stability of nucleus. Determine the stability of nucleus. For lighter elements, the number of neutrons required for nuclear stability is almost equal to the number of protons. So up to atomic number 20, that is Z is equal to 20, N/P ratio required for stability is 1. N/P ratio required for stability is 1. That is, up to atomic number 20, the number of neutrons required for a stable nuclei is equal to the number of protons. But as the number of protons increases above 20, that is, if the atomic number is greater than 20, then more neutrons are required to compensate the strong electrostatic repulsion between large number of protons in a small nuclear volume. So for Z greater than 20, N by P ratio required for stability is greater than 1. To illustrate it further, a stability band is obtained by plotting the number of neutrons versus number of protons here. If we put the limit of 20 here and here, up to atomic number 20, the number of neutrons required for a stable nucleus is equal to number of protons. But above atomic number 20, more neutrons are required for stability than the number of protons. So the curve will bend towards y-axis and we obtain this type of curve. If we extrapolate this as a straight line, this should have been the straight line. But the actual stability band is this. It is not a fine line, rather it is a band. So it is like this. And this we call band of stability. So for stable nuclei, their N by P ratio must fall in the band of stability. If for any nuclei N by P ratio does not fall in the band of stability, then it will decay. And during the decay, interconversion of neutrons to protons will occur, giving off some radioactive rays. So that we are going to determine that how the unstable nuclei, how the radioactive isotopes are going to decay. So let us take the case one by one. If N by P is greater than 1 and Z is less than 20. So we are talking about the lighter isotopes where N by P ratio required for stability is 1. So if N by P is greater than 1, it means neutrons is in excess. Then what will happen? Some of the neutrons will be converted into protons. Some of the neutrons has mass number 1, charge 0, will be converted into protons which has charge 1 and mass also 1. For a balanced nuclear reaction, mass number and charge number must be balanced. So here we have one more charge. To balance that, we'll have to take a beta particle which is nothing but an electron. Now -1 + 1 0. So mass number is 1. So it will undergo beta decay. So if N by P ratio is greater than 1, it will undergo beta decay. If number of neutrons is more than number of protons, it will undergo beta decay. If we want to take a real example, now let us take a case of N16, nitrogen 16. Here we have 7 proton and 9 neutron, which is greater than number of proton. So it will decay by beta emission. Some of the neutrons will be converted into proton by this nuclear reaction. It will undergo beta decay, and here we have 7, so minus 1 plus 8. 8 is the atomic number of oxygen. So oxygen will be produced, and this is beta decay. One more case we can take here is decay of potassium 40. Here again we have 19 proton but 21 neutrons. Again, neutron is more than proton, so it will decay by beta emission, and minus 1 plus 20, 19, so calcium will be produced. A very common example of beta decay is decay of carbon 14, which we use in C14 dating in determining age of fossil. Carbon 14, again we have 6 proton, 8 neutron. So it will decay by beta emission, giving nitrogen 14. So that is how the N by P ratio is balanced. Neutron proton numbers are balanced in case of radioactive isotope. The second is N by P ratio is less than 1. N by P ratio is less than 1, and Z is less than 20. Z is less than 20. Here we have more protons than required. Then what will happen? Some of the protons will be converted into neutrons in order to become stable. So protons will be converted to neutrons, and this conversion can occur in two different ways. One, by positron emission,